Welcome to Beyond the Comfort Zone, Talking Shit with KING-KAMBUF. Today, we are opening the syllabus for the Design and Build School of KING-KAMBUF, or DBSK as you'll hear us call it. We're diving right into a really essential graduate module.
Yeah, we are. We're getting into ARC 533, which is Building Science and Enclosure Systems.
And this feels like a critical one.
This deep dive is absolutely crucial for anyone even remotely involved in urban housing development.
Yes.
And we're not talking about aesthetics here, not at all. We are talking about the fundamentals of, survival engineering, really.
Survival engineering,
Yeah.
okay. And the focus specifically is on mixed mode ventilation and these high performance enclosures for, the kind of building you see everywhere.
Urban mid-rise podium block.
Yeah.
Exactly.
So the mission then, as the DBSK faculty lays it out, it sounds simple on the surface, but I'm guessing it's not. It's about figuring out how to give these structures lungs.
That's the perfect word for it, lungs. How do you make a building that's dense, multi-story, but also resilient, energy efficient, and genuinely breathable?
Yeah.
And to anchor this whole conversation, we're going to fix every single design decision. And I mean everything. From the type of window you pick, to the complexity of your control system, to one single pretty terrifying stress test scenario.
Okay, let's hear it. Paint the picture for us.
All right, so imagine your resident. Let's call her Eleanor. She lives on the 5th floor of this new building you've just designed.
Okay.
And she is trying to survive a brutal 5-day heat wave. Temperatures are way above average. But that's not all. It's also coinciding with massive regional wildfire smoke that has just blanketed the entire city.
Which is becoming more and more common.
Frighteningly common. And then just to really push the system to its limit, we're going to throw in a complete 12-hour grid failure right in the middle of all of this.
Wow. Okay, so that is the ultimate test, isn't it? That's passive survivability right there. If Eleanor isn't safe and, at least relatively comfortable during that power outage,
Then you haven't designed a high-performance building.
you've designed a very large, very expensive hazard.
Precisely. And that extreme scenario, it forces us to answer what we call the 3 survival questions. They basically frame our entire deep dive today and define your building's whole relationship with air.
Okay, so the first one has to be, when the world outside turns hostile, where does safe, fresh air actually come from?
Right. And then second, where does all the bad air, the stale, polluted hot air, where does it go? How do you intentionally get it out?
And then the third, which feels like the most critical one given the scenario, what happens to the air quality, to the temperature when the grid just fails?
Exactly.
Yeah.
You have to be able to visualize these flows from the very first sketch.
Hmm.
If you're in the DBSK classroom, you're grabbing 3 different colored pens.
Okay.
Blue arrows, they show air moving horizontally through the apartments. That's your basic cross ventilation.
Simple enough.
Then you grab the red pen. The red arrows show the vertical movement. That's the STAP effect, natural buoyancy. Cool air comes in low, it warms up, and then it exits high up through shafts or an atrium.
That's the building's natural engine.
That's the engine. And finally, green arrows. Those represent your controlled, filtered mechanical intake and exhaust. You usually see them on the roof or at specific points on the facade. Every single technical choice we talk about has to support the movement of these colored arrows. It has to answer that one question. How does my building breathe under stress?
All right, let's unpack that challenge. We'll start with section 1, determining feasibility. Because before we even talk about walls or windows, you have to do this brutally honest assessment of the site and the climate.
Yes.
It's about getting past sort of the architectural vibes and getting a real snapshot of the context.
Absolutely. You cannot design a naturally ventilated building just because you want one. That's a recipe for disaster. The site and the climate, they have to cooperate. So we focus on 5 of these external context factors that tell you if you're looking at a green light strategy.
Full mixed mode.
Right. Or yellow light, where you need a hybrid system.
Yeah.
Or if it's a red light, meaning you have to seal it up and rely on mechanical.
Okay, let's start with the most basic one, but let's be really precise about it. Dry bulb temperature.
Okay, so dry bulb is just what you'd think. It's the air temperature you read on a normal thermometer. But its real purpose in this kind of design is to map the seasons. We need to know how bad the extremes are.
Your peak heating and peak cooling loads.
Exactly. But for natural ventilation, the real golden zone is the shoulder season. Those weeks or months in spring and fall where the temperature is mild enough that just opening a window gives you all the comfort you need.
So the longer that shoulder season is, the more viable the whole strategy becomes.
It becomes much more viable. But temperature on its own, as you always have to emphasize, is almost a useless metric without its partner, humidity. This one factor can change the entire design equation.
It changes everything. Why?
Okay, look at the difference between, say, a hot, humid climate like you'd find in the coastal southeast U.S. and a hot, dry climate like the desert Southwest.
Two totally different kinds of heat.
Totally different. In that hot, humid place, once the humidity gets above, say, 60 or 70%, your body's cooling mechanism, sweating, it just stops being effective.
Right. The sweat doesn't evaporate.
It doesn't evaporate.
Yeah.
So you can have a strong breeze blowing through the apartment, but the air feels heavy, sticky, just deeply uncomfortable. You're forced to turn on the mechanical cooling and dehumidification much, much sooner.
Okay, so now contrast that with the hot, dry region.
In the hot, dry region, a temperature of 82, maybe even 85 degrees Fahrenheit can feel quite comfortable if you have good air movement.
Because the evaporation is working overtime.
Exactly. The dry air passing over your skin actively pulls moisture away, cooling you down. So this extends that green light comfort band for natural ventilation by a huge margin. If you don't account for humidity, you might promise your residents this beautiful natural ventilation that, in reality, they just can't tolerate for huge parts of the year.
Now, this is where it gets really interesting for designers, I think. The diurnal swing. I've always been fascinated by the architectural power you get from that day-to-night temperature shift.
It is architectural power, just waiting there to be harnessed. If your climate has a large diurnal swing, and that means the temperature reliably drops by, 15, 20 degrees Fahrenheit or even more overnight, you have the perfect setup for what we call night flushing.
Okay, so how does that work in a practical sense in a mid-rise building?
You open up the building's vents or windows during those cool night hours, and you're just pulling that low-temperature air right through the structure. And you're not just cooling the air in the room.
You're cooling the structure itself.
You're actively cooling the high thermal mass components, the concrete slabs, the walls. That pre-cooled mass then acts like a massive thermal sponge the next day. It soaks up the heat, delaying the need for mechanical cooling, and it lowers your peak load when the sun is blasting the facade.
But if you don't have that swing?
If the night stays almost as hot as the day, then night flushing gives you almost no benefit. It's just a really honest, early check on your design's feasibility.
Okay, so we've covered the static conditions, temperature, moisture. Now let's talk about movement. Prevailing winds. Designing a building that works with the wind.
Yeah, and this requires real data, local data, not just guessing. Where does the wind actually come from, and does it change with the seasons? Good designers will orient the building to catch these prevailing flows on the longest facades.
I've seen courtyards used for this.
A courtyard is a classic tactic. You can use it not just for light, but as a funnel. By shaping the wings of the building, you can actually accelerate airflow into those interior spaces, which really enhances your cross-ventilation potential.
And if you get it wrong...
If you put a massive, solid wall right up against the prevailing wind, you've just blocked your best and cheapest natural cooling resource. It's a huge missed opportunity.
And now for the final reality check. The one factor that can just cancel out perfect weather.
Noise and pollution.
The ultimate veto.
It is. It's the external veto power. You could be in a perfect 72-degree low-humidity shoulder season, a complete meteorological green light, but if your building is right next to a 6-lane freeway, the noise and the particulate matter mean opening the window is simply not an option.
And let's get specific about that pollution. Why is PM 2.5 so critical here?
Okay, so PM 2.5 refers to particulate matter that's smaller than 2.5 micrometers. These are incredibly tiny particles from car exhaust, from industry, or from wildfire smoke. They're small enough to get deep into your respiratory system, even your circulatory system.
So they cause real health damage.
Serious health damage. If the outdoor PM 2.5 levels are high, opening your window means you are trading thermal comfort for a long-term health risk. And at that point, your climate traffic light has to turn red instantly.
So let's detail that analogy. This is the framework the DBSK assignment demands, right? You have to place your project honestly on this spectrum.
Yes. The green zone, that's where full, natural, or mixed mode is your primary strategy. You've got great climate conditions, a clean, quiet site. You can rely on operable windows and the stack effect for most of the year. It's the low-hanging fruit of energy savings.
Then we hit the yellow zone where things get a lot more complicated.
The yellow zone demands a sophisticated hybrid strategy. You have to switch between modes intentionally. This might be a seasonal switch, so natural ventilation is only allowed in spring and fall.
Or it could be based on time.
Time of day, exactly. Using that night flushing we talked about, but sealing the building up during the hot or polluted midday hours. Or you can get really complex with a zonal strategy, where different parts of the building follow different rules.
Which brings us to red.
A red light site demands a mostly sealed building. Your site constraints, the noise, the pollution, maybe seasonal dust storms, they just prohibit relying on open windows. Your primary design response has to be a highly efficient mechanical ventilation with mandatory high-grade filtration.
The key takeaway here seems to be about honesty.
It's all about honesty. The DBSK takeaway is to resist the temptation to promise this heroic natural ventilation if your site just flat out doesn't support it. That honesty up front is what dictates the building's resilience later on.
Okay, so now that we know what the outside world is throwing at us, we move inside and talk about the defense mechanism. Section 2. The enclosure as an environmental machine. We're building the shell that manages all these flows.
And it is an active machine. It's not just cladding. It operates based on an absolutely immutable hierarchy. And if you fail to respect this order of operations, your whole building science assembly will fail.
And that order is water, then air, then vapor, then thermal.
Water, air, vapor, thermal. Get that order wrong and you're looking at consequences far beyond just energy loss.
No, so let's start at the top. Water control. Why does keeping out liquid water trump absolutely everything else?
Because water damage is immediate, it's structural, and it is incredibly expensive. If bulk liquid water rain, snowmelt, gets into your assembly, it fails instantly. The critical design element here is what we call the drainage plane, or the rain screen principle.
So the outer layer can get wet?
The outer layer is allowed to get wet.
Yeah.
But behind it, you must have an airspace and then a continuous secondary waterproof layer. That's your drainage plane. It catches any water that gets past the cladding and directs it back out through flashings and weep holes.
You're designing for failure.
You must design for failure. Your overhangs, your meticulous detailing of flashings around every single opening, those are your non-negotiable insurance policies. If you don't manage bulk water, you get mold, you get rot, and your building becomes an unhealthy liability.
Okay, moving on. In the lecture, the air control layer is called the big one for mixed mode success. We talk a lot about R value for insulation, but air tightness is actually more critical. Why is that?
It all comes down to the kinetics of energy and moisture transport. The air barrier's main job is to make sure the air inside stays inside and the air outside stays outside. When we get to high levels of air tightness, we ensure that air only moves through our controlled paths, our blue, red, and green arrows.
But there's a conflict here, right? I imagine this is a real battle for students and for architects in the field. The cost of getting to truly high levels of air tightness. How do you convince a developer to chase something like a passive house target when the code is much looser?
That is the core challenge of the job. You have to sell it based on risk reduction and HVAC sizing. An air leak carries a massive amount of energy and moisture with it. Uncontrolled air leakage can account for 30, maybe even 50% of your total energy use in a mid-rise building.
That much.
That much. And even more importantly for the structure itself, uncontrolled air can transport 50 to 100 times more moisture into your wall assembly than simple molecular diffusion can.
So an air leak is basically a fire hose for water vapor.
It's a fire hose, exactly. If you have an air leak in winter, warm, moist interior air shoots into the cold part of the wall, it flash condenses and you get rapid, massive mold growth or decay. By building a high-performance air barrier, you fundamentally de-risk the entire structure and you stabilize your mixed-mode system.
And it saves money on the HVAC.
It saves a lot of money. Your HVAC system doesn't have to constantly fight all this uncontrolled infiltration, which means you can buy smaller, cheaper, and more efficient equipment. That's your financial argument for airtightness right there.
Okay, next in the hierarchy is vapor control. This is the layer that seems to confuse every student at first. Why is putting the vapor barrier on the wrong side such a huge structural liability?
This is where climate context is absolutely essential. A vapor barrier, it restricts the molecular movement, the diffusion of water vapor. In a very cold climate, the rule is to put the vapor barrier on the warm side of the insulation, on the interior.
To stop moisture from getting into the cold wall.
Exactly. But in hot, humid climates, that rule completely reverses. Because in a hot, humid climate, the primary moisture drive is often inward, from the hot, humid outside to the cool, dry inside. If you put a traditional plastic vapor barrier on the interior, you prevent any moisture that does get into the wall from drying back into the conditioned space. You trap it. And trapped moisture invites mold.
So this is why we're seeing more of these smart membranes.
Yes, smart membranes or vapor-open assemblies are becoming the standard for high-performance design.
So what is a smart membrane actually doing?
It's a variable permeance material. It basically changes its permeability depending on the humidity level. When the wall is dry, the membrane is relatively tight and acts as a vapor retarder. But if it senses high moisture content inside the wall, it becomes much more vapor open, allowing that trapped moisture to diffuse and dry out.
So it's a risk mitigation strategy.
It is, but it only works, and this is critical, if you have a perfect continuous air barrier underneath it.
Finally, we get to the insulation strategy, thermal control. And the focus here isn't just on R value, it's on continuity.
Continuity is everything. The biggest failure point for insulation is the thermal bridge. A thermal bridge is any path of high conductivity that just bypasses your insulation layer.
Like a concrete balcony slab.
The classic example. If a solid concrete slab just punches right through your wall assembly, it acts like a massive heat fin. It just bleeds heat out in the winter and sucks it in during the summer, and it can dramatically reduce the effective R value of your entire wall.
So the solution is continuous exterior insulation.
Yes. Wrapping the entire structure in a continuous layer of insulation on the exterior mitigates almost all of that thermal bridging. And then we have to tune the window performance too. We talk about U value and SHGC.
U value is like a thermos, right? How well it holds heat in.
Perfect analogy. You want a low U value. SHGC, the solar heat gain coefficient, is like sunscreen. It's the fraction of solar radiation that gets let in as heat.
And you tune these based on which way the window is facing.
Exactly. On the south facade, you probably want a slightly lower SHGC to minimize that summer heat gain. On the north, where there's no real solar gain to worry about, you just optimize for the lowest possible U value. You're tuning the envelope to the specific site.
And the litmus test for all of this, the tool the DBSK lecture really pushes, is the continuous path test.
It's mandatory for our students. You grab a marker and you trace the line of your air barrier. It has to wrap seamlessly around all four sides of the building, across the sheathing, over the foundation, under the roof, and critically, it has to continuously wrap the perimeter of every single window.
And if your pen has to lift off the page?
If your pen has to lift, you have design flaw. And that flaw will show up as an air leak, an energy bleed, and it will make your whole system unstable. It will compromise your ability to answer those three survival questions.
So if the envelope is this tight machine, what are the performance targets we should be aiming for, beyond just meeting code?
We have to aim significantly higher than code. IECC, HHRA, 90.1, those are the floor, not the ceiling. For a resilient mid-rise, we're looking for really aggressive wall U values, tuned glazing, and a clear, verifiable air tightness target, often 1.0 ACH at 50 PAR or even better. And that demands rigorous quality control and field testing, like blower door tests.
Because if you don't aim higher, the whole mixed mode system is just too unstable.
It will never be stable enough to justify the complexity of the controls you need to run it.
Okay, so we've built the tight, continuous machine. Now we're in section 3. Strategies for breathing mixed mode typologies. This is where we activate that machine.
Right, we're moving from the static design elements to the dynamic operational modes, natural, mechanical, and that hybrid combination that tries to leverage the best of both.
Let's start with the natural ventilation tactics, the ones that rely just on the physics of the site. First up, cross-ventilation.
Cross-ventilation is the simplest idea, but it's often the hardest to achieve in these dense urban buildings because of their deep floor plates. You need openings on at least 2 different facades, and ideally you want short, wide apartment units so the wind can push air in one side and pull it out the other.
It's driven by wind pressure.
Primarily, yes.
Yeah.
But for deeper units or, say, shared public spaces, you have to rely on the power of the stack effect.
Which is buoyancy.
It's buoyancy driven by heat. It's a vertical thing. Cool, denser air enters low, maybe a ground floor lobby or dedicated shafts. It gets warmed up by people, lights, the sun, and it becomes less dense. It rises, and then it's exhausted at a high point, like a roof cap.
But this requires dedicated architectural infrastructure. It doesn't just happen by accident.
It absolutely requires it. You have to design intentional vertical pathways, atriums, dedicated air shafts, maybe even specific stairwells that are part of the airflow strategy. If you don't design those vertical stacks, the stack effect will just try to pull air through random leaks in your floor slabs and utility chases, which, again, compromises your air tightness. The red arrows have to be intentional.
Okay, so now when that climate traffic light turns yellow or red, we have to rely on mechanical systems. And the core of a modern system is often the DOAS.
DOAS, which stands for Dedicated Outdoor Air System. This is a really vital modernization. Historically, HVAC systems just mixed ventilation air and heating and cooling air altogether.
Which made it hard to control air quality.
Very hard. The DOAS separates those functions. It has one job,
Okay.
bring in 100% fresh outside air, treat it, temper it for temperature, maybe humidity, and supply it to the occupied spaces. The actual heating and cooling is handled separately. This separation gives you precise control over your fresh air supply.
And to avoid just jumping all that conditioned air outside and wasting massive amounts of energy, we need recovery systems.
HRVs and ERVs, heat recovery and energy recovery ventilators. They are completely non-negotiable for a high-performance building. They work by capturing the thermal energy, the heat, from the stale exhaust air and transferring it back into the incoming fresh air stream.
What's the difference between an HRV and an ERV?
So an HRV transfers only sensible heat, just temperature. An ERV transfers both sensible heat and latent heat, which is moisture.
So the choice depends on the climate.
Exactly. If you're in a cold, dry climate, an HRV is often fine, but in a mixed or a hot, humid climate, an ERV is essential because it recovers some of that cooling energy that's tied up in dehumidification. It stops the incoming fresh air from being too dry in the winter or too humid in the summer.
Let's go back to our stress scenario. Eleanor, dealing with that wildfire smoke, filtration becomes mandatory. What's the specific requirement there?
To effectively fight wildfire smoke or deep urban pollution, you must specify filtration that can handle PM2.5. This usually means a minimum of MRV13 filtration, often even higher, like MERV14, in regions that are prone to smoke.
And MV13 is the standard for it?
It's the standard for capturing common viruses and, critically, a high percentage of those submicron smoke particles. If your system can only handle MV8, you are literally trapping residents inside with dangerously dirty air during a smoke event. This is a matter of life and breath.
Okay, so the real design genius comes in combining all these, the hybrid or mixed mode sweet spot. How does the building actually choose which mode to be in?
It uses specific switching mechanisms. There are three primary types that dictate how the building transitions.
First is seasonal.
That's the simplest. During the mild shoulder seasons, the control system allows natural ventilation. In peak summer or peak winter, it seals the building and runs the mechanical system.
Second, time of day.
Right, this is to maximize the effect of that diurnal swing. The building is sealed during the high-load, high-pollution daylight hours. Then, as the sun sets and the air cools, the system initiates that controlled night flush to pre-cool the thermal mass for the next day.
And the third, the zonal strategy, which integrates that whole traffic light concept directly into the controls.
This is maybe the most difficult to execute, but it's the most responsive. So imagine a building with two different faces. The units facing a quiet courtyard get a green or yellow light. They're allowed frequent natural ventilation.
But the units on the street side?
The street-facing units are constantly battling traffic noise and exhaust. They are locked into a red light status, and they rely almost entirely on highly filtered mechanical air. The control system has to manage these two zones completely independently.
This brings us to the 3 clarity tests for DBSK students. You have to be able to diagram this perfectly.
Test 1. Where does the natural air enter and exit? Show me the blue and red arrows. Show the specific openings and routes. Test 2. Where does the mechanically filtered air enter and exit? Show me the green arrows, the DOAS supply, the HRV exhaust.
And test 3 is the most complex.
Test 3 is the logic. Under what specific conditions, temperature, time, and pollution levels is each mode allowed to operate? If you can't answer that with precise logic, like natural mode is permitted when outdoor temp is between 65 and 78 and PM2.5 is below 15, then your design is just arbitrary. The building won't know how to breathe when conditions change.
We've established the machine and the breathing strategies. Now, Section 4, the marriage of systems envelope HVAC integration. This is about that permanent, necessary feedback loop between the wall and the mechanical system.
You cannot design these in isolation. The DBSK mandate is crystal clear on this. The wall is not just a thermal barrier. It is the first and most critical component of the HVAC system. Decisions you make on the envelope have monumental, lasting consequences for the HVAC infrastructure.
And the most immediate of those consequences is load reduction. This is where we talk about the cleanest energy.
The cleanest energy is every single kilowatt hour you never have to generate in the first place. A tightly insulated, airtight, and well-shaded enclosure will drastically reduce the heating and cooling loads required to maintain comfort.
So what does that mean in practical terms for the designer?
It means you can right-size the equipment. Instead of needing this massive 50-ton chiller bank to handle the heat pouring into a leaky code minimum building, your high-performance building might only need a 30-ton system.
That's a huge reduction.
It's a 40% reduction in capital cost, in physical size, maintenance liability, and long-term energy use. That efficiency reduction is your best financial argument for investing heavily in the envelope up front.
So that makes the upfront cost of, say, continuous insulation much easier to swallow because you're offsetting it with cheaper, smaller mechanical equipment.
Exactly. It changes the whole conversation. It's no longer how much does that wall cost. It's how much does that wall save us on mechanicals and operating costs for the next 50 years.
Beyond the money, the envelope has a profound effect on human comfort. Let's expand on the comfort triad. Most people only think about air temperature.
Right. The comfort triad defines thermal sensation. It's made up of air temperature, mean radiant temperature, or MRT, and air speed. Air temperature is what the thermostat says. Air speed is how fast the air is moving.
But MRT is the game changer here, and that's the one the envelope controls.
MRT is the average temperature of all the surfaces surrounding you. So think about standing next to a big, poorly insulated window in the winter.
You feel cold even if the room is warm.
You feel chilly. Even if the thermostat reads 72 degrees, your body is radiating heat out to that cold glass surface. That's low MRT, creating discomfort.
So what does a high-performance continuous envelope do to the MRT?
It ensures that all the interior surfaces, the walls, the floor slab edges, the window frames, stay very close to the actual air temperature. And when your MRT is high and stable, people feel comfortable across a much wider range of air temperatures. We call this widening the operational comfort band.
Which is the key to making mixed mode work.
It is absolutely key. If a resident feels comfortable when the air is 78 degrees because the walls aren't radiating heat onto them, you can keep the mechanical cooling off for much, much longer. That operational flexibility is the true power of the high-performance envelope. It lets the natural breathing strategies dominate for more hours of the year.
But none of this adaptive system works without a very intelligent brain, control logic, and sensors. Mixed mode is really a controls problem, isn't it?
It is, fundamentally. The control system has to be fed constant, precise information to decide which mode the building should be in. We need physical sensor inputs.
So starting with the most basic interlocks.
Window contacts. Absolutely essential. The system has to know, in real time, if a window is open. That information triggers the interlocks, which are your critical energy protection. They disable the heating and cooling supply to that specific zone the second the window opens.
So you're not trying to air condition the entire neighborhood.
Exactly. That's just massive energy waste.
And for health and resilience, we need to move beyond temperature to IAQ sensors, indoor air quality.
Correct. We need to monitor two things specifically. First, Euro sensors. Carbon dioxide is an excellent proxy for occupant density and stale air. High Euro means you need more fresh air. Second, and vital for our stress scenario, are PM2.5 sensors.
So how does the PM2.5 sensor integrate with the operational modes?
If the outdoor PM2.5 sensor spikes above a preset health threshold, say 35 micrograms per cubic meter, the control system immediately shifts the entire building, or at least that zone, into mode 3.
Let's detail those three operational modes now, defined by that control logic.
Okay, mode 1 is natural. Sensor data confirms low Euros inside, low pollution outside, and mild temperatures. Windows are permitted to open. The duet is running at a minimum, or maybe it's off entirely. The building is breathing naturally with the blue and red arrows.
Okay, then mode 2, mechanical.
Outdoor conditions are too hot, too cold, or too humid. Windows are instructed to remain closed, the interlocks are engaged, and the full DOS system, coupled with the HRVs or ERVs, runs at the required ventilation rate, providing high-quality conditioned air. That's your green arrows.
And then mode 3, emergency resilience.
This is triggered by high PM2.5 from wildfire smoke or extreme heat event. Windows are locked or strongly advised to be closed. The system shifts to maximum filtration MERV V13 plus on the DOS supply, and crucially, it often slightly pressurizes the interior spaces.
Why the pressurization?
When you slightly pressurize the interior, any remaining small cracks or leaks in your air barrier will force air out of the building. This prevents unfiltered dirty air from being sucked in from the outside. So that intentional marriage of systems means your high-performance wall becomes the container and your HVAC system becomes the controlled air pump, guaranteeing safe indoor air quality when Eleanor on the 5th floor needs it the most.
And that brings us to Section 5, beyond efficiency, resilience, health, and equity. This is where all those technical decisions we just discussed, they transition into these profound social and ethical responsibilities.
Yeah, the DBSK program really emphasizes that architects and engineers, you're creating a covenant with the occupants. And the ultimate measure of good design is passive survivability. If the building loses power, who is protected and for how long?
So let's run that scenario again. The 48-hour outage during a peak summer heat wave. Let's visualize that temperature curve comparison.
Okay, in a code minimum, building leaky, poorly insulated, full of thermal bridges, the indoor temperature spikes dramatically. The building acts like a greenhouse, an oven. Heat is pouring in from the outside, and the radiant temperatures from the interior surfaces soar.
So those top floor west-facing units?
They could hit dangerous, even lethal temperatures within just 8 to 12 hours.
Yeah.
The building becomes immediately unsafe when the grid fails.
Now, contrast that with the high-performance enclosure we just designed.
Because of the continuous exterior insulation, the thermal mass inside is protected. Because of the extreme air tightness, hot air infiltration from outside is minimal. So the indoor temperature rise is severely attenuated. It's a slow, shallow curve over 48 hours.
It's still climbing.
It's still climbing, but it might stay within a survivable range for 24 or even 48 hours. That buys Eleanor critical time for the grid to be restored or for her to evacuate safely. The envelope becomes her life support system.
So passive survivability is directly tied to that initial investment in the wall. If you didn't invest in airtightness and insulation, you're signing your residents up for immediate danger during a heat wave.
Absolutely. The structural safety is directly linked to the energy performance of the envelope. And survivability isn't just about heat. It's about air quality during non-power grid failures, like that wildfire smoke scenario.
Right. Indoor air quality during stress. If that high-grade mechanical filtration doesn't work, the building just becomes a trap.
It is the ultimate consequence of falling in love with the idea of natural ventilation without acknowledging the harsh reality of urban pollution. If your building can be naturally ventilated but lacks the sophistication to seal up and filter when PM 2.5 spikes, you've essentially trapped your residents in a hostile environment. You're forcing them to choose between breathing particle-laden air and opening a window.
Which is no choice at all.
It's no choice at all. It means you have to constantly test and verify the filtration systems, make sure they're maintained and operating correctly.
This leads us straight to the required equity check, which is arguably the most important part of the entire DBSK assignment package. You have to scrutinize your design decisions for how they distribute comfort and resilience.
This forces the architect to confront the potential for creating a two-tier system of comfort right inside their own building. We have to actively ask, are the quietest units, the ones with the best cross-ventilation, the ones facing the protected courtyard, are they reserved only for the market rate or the high-rent parts of the building?
And inversely, where are the disadvantaged units being placed?
All too often, they're placed on the noisiest facades, the hottest west-facing exposures, or right under the roof slab, which takes the biggest heat load during an outage. If your subsidized housing or elder housing units are all on the side battling traffic and pollution, requiring them to rely solely on mechanical air while the high-rent units get to enjoy a quiet, natural night flush, you've codified inequity into the very structure of your building.
And the lecture encourages students to do the scenario sketch challenge on their own plans.
Yes, to literally map the consequences, draw the sun path, draw the noise contours, identify which units get the optimal mixed mode performance and which are forced into perpetual mode 2 or 3 operation. The designer has to push back against the site constraints or the economic pressures that create these unfair divisions.
Because comfort, safety, filtered air, these should be for everyone.
They should be distributed fairly to all residents, regardless of their rental tier or their location in the building. Resilience is measured by who survives comfortably when systems fail, not just by how many kilowatt you saved.
This means you have to think past the schematic design phase and into the real-life safety consequences of your wall and ventilation choices. The building should be an engine for equality, not an accident of privilege.
Absolutely. And the technical choices, the continuous insulation, the high MRV filters, the intelligent interlocks, those are the tools for achieving that social mandate. If you don't design for resilience and equity, the structure is just an elaborate container. It's not a responsible home.
So as we wrap this up and synthesize this rigorous path we've just walked through the DBSK curriculum, what's the unifying principle?
It's undeniable, really. It's enclosure plus intentional air management and verifiable safety.
All that technical rigor, the tight air barrier, the tuned windows, the sophisticated duas, it all transforms into a measurable promise of health and survivability for the people inside. And for everyone following along in the Design and Build School of KING-KAMBUF, the final requirement for the ARC 533 assignment. It acts as our actionable mandate, our synthesis.
Right. The comprehensive design package has to include 4 essential elements that prove you understand this integration. First, that mandatory climate and context snapshot. You have to honestly place your project on that green, yellow, or red traffic light spectrum.
Second, the detailed enclosure cut section. This has to clearly illustrate that hierarchy of control layers: water, air, vapor, and thermal. And it has to prove, using that continuous path test, that those layers are uninterrupted.
Third, at least 2 diagrams of mixed mode operation. A plan and a section view, clearly labeling the flow paths for both natural, your blue and red arrows, and mechanically filtered air, the green arrows. The building has to be transparent about how it breathes.
And finally, the essential piece, the performance and equity memo. This is where you justify your choices, both against the code baseline and against an ethical standard.
That memo has to answer 3 core questions. These are the mnemonics you should take away from this entire deep dive. 1, how does this strategy measurably reduce the building's energy use intensity compared to a code minimum baseline?
2, how does the design ensure the building performs safely and survivably during a 24 to 48-hour power outage in peak heat or peak smoke?
And perhaps the most difficult question of all, how has the designer actively worked to avoid creating a 2-tier system of privileged and disadvantaged units, ensuring a fair distribution of comfort and resilience across the entire structure?
It all comes back to that ethos.
The DBSK ethos, yes. In the creation of urban housing, enclosure and air are not aesthetic choices. They're not style. They're covenants you make with the people who will live inside your buildings. You are designing a shelter, a refuge, and a guarantor of health.
Go make this knowledge worthy of that immense trust.
The lesson is complete. Now go build something that truly breathes.